Okay, so now let's see the global posedness in the theorem. Okay, so the solution of the initial value problem of the Boson Stars equation that we'll derive um, in the last theorem for local posedness um, is global in time. Okay, that is to say, we have that t is equal to infinity. This holds provided one of the following conditions. So when we will have global solutions, well, first, if lambda is greater or equal to 0, okay. 2, if lambda is negative, but also we will need that the norm squared u naught squared 2 is less than, let's say, q squared 2, okay, where q is in h1/2 or 3 is a strictly positive solution ground state, okay, of, well, minus Laplacian q plus lambda x convolution q squared. This has to be inside. So q minus q, okay, and moreover, we have the estimate norm q squared 2 is greater than 4, 5 absolute value of lambda, okay. Okay, so the first step, we're going to settle the conservation of energy and charge, okay. Conservation of energy will be EU, by definition, 1/2 or 3 U you conjugate minus Laplacian plus m squared ux bx plus 1/4 or 3 lambda e minus mu x convolution u squared of the f x u x, so the value squared dx. This is conservation of energy, and now of charge, more simple, and u is by definition integral in R3 of ux squared dx, okay. Okay, so a lemma, the local in time solutions that we established in the first theorem, obey conservation of energy on charge. Okay, so this is to say that E of ut is equal to E of u naught, and well, n of ut will be equal to u n of u naught. Okay, this is for all t 0 t. Okay, so what we want to prove is that d dt and ut equals to 0, and the same for e ut. Okay, so for the conservation of charge first, remember we have ut equal to the population and the square root u of u. If we take the I to the other side, we will obtain minus I square root u minus I f u. Okay, so we've got n u of 3ux squared dx. Okay, and well, this is x and t, no? And well, this is 3 u conjugate. Okay, and well, we can say that this is equal to the scalar product of u. Okay, in, well, hidden space L2, we can say. So what do we want to know? What happened with d dt and of u? Okay, so this will be equal to d dt of uu, and this will be equal to ut, derivative in t, u plus ut. Okay, so let me call this a and use it. Now when we put ut, we will put this. So we will have that this is equal to minus I a u minus I f u, okay, comma u plus, well, u, and then again minus I a u minus I f u. Okay, so this will be equal to minus I a u plus minus I f u plus u comma minus I a u, here with an I, and again plus u minus I f u. Okay, close here. Okay, so now let's take the constants out. I a u plus I f u plus, well, minus I u a u minus I u f u. Okay, there. So a is self-adjoint. So this term, I can put it here and it will stay all the same. These two terms, this one and this one, will go. But what about these two? Okay, so let's see. So this is f of u, And notice that we have absolute value of x, absolute value of x, absolute value of u is a real number, lambda is a real number, so this is real. Okay, what happens to this one? Okay, so if we have, for example, alright, well, the I doesn't matter, but we have if u and u if u. These are the two terms that we have. So this will be the integral if you conjugate, okay, u, and well, let's make some of them. So we have that is this conjugate will stay the same. So we got what we got in the parentheses, that is real, and u conjugate multiplied by u, which will give us well, the parentheses multiplied by u squared. And now what about u if u? Well, we will have once again u conjugate if u, well, if u is the parentheses multiplied by u, parentheses that is real, okay, and multiplied by u, this will be again u squared. So we have this is the same, okay. So these things are the same. We finally get that d dt and u is equal to 0, okay. So we have conservation of charge, okay.